Welcome to today's session. We'll be diving into problem number 1367, titled Linked List in Binary Tree. This problem challenges us to explore the integration of linked list traversal within the structure of a binary tree. Get ready to learn and grow as we tackle this together. In this problem, you're given two data structures, a binary tree and a singly linked list. The task is to determine whether the linked list appears as a subpath within the binary tree. A subpath is defined as a sequence of nodes that begins at some node in the binary tree and follows a strictly downward path, moving only to child nodes, with the values of the nodes in this path matching the values in the linked list in the same order. For the inputs, we have the head of the linked list, which contains a value and a reference to the next node, and the root of the binary tree, which contains a value and references to its left and right child nodes. The output is a Boolean value, true if such a subpath exists, and false otherwise. The output is true if the linked list can be matched as a subpath in the binary tree, and false if no such path exists. Let's look at some examples to clarify this further. In the first example, the linked list contains the sequence 4, 2, 8, and we are tasked with finding this sequence in the given binary tree. The binary tree is visualized as shown, and we can see that there is indeed a downward path starting from the leftmost 4, then moving to 2, and finally reaching 8. Since this path matches the linked list exactly, the output is true. Now, let's focus on the linked list itself. Here, the linked list is represented as 4-2-8, and as we just noted, the binary tree contains a matching downward path with the exact sequence of values, 4-2-8. This confirms that the linked list is a subpath of the binary tree. Moving to another example, consider the linked list 1, 4, 2, 6. The binary tree remains the same as before, and we need to check if there exists a downward path matching this linked list. For the linked list 1-4-2-6, we see that such a path exists in the binary tree. Starting at the root node, which has the value 1, we can follow a downward path to 4, then to 2, and finally to 6. This sequence matches the linked list exactly, so the output is true. However, in the third example, the linked list is 1, 4, 4, 4. Here, it is impossible to find a downward path in the binary tree that matches this sequence. While the binary tree does contain multiple nodes with the value 4, no path contains 3 consecutive 4s. As a result, the output in this case is false. Finally, let's consider some edge cases. If the linked list contains only one node, we simply check if there is any node in the binary tree with the same value. If the binary tree contains only one node, the entire linked list must match the single node for the output to be true. If the linked list is longer than the height of the binary tree, it's impossible to find a match, so the output is false. Lastly, if the binary tree contains duplicate values, the function must handle multiple potential starting points for the linked list and ensure the values match sequentially along a single path. These edge cases ensure that our solution is robust and handles all possible scenarios efficiently. To solve the problem of determining whether a linked list exists as a subpath in a binary tree, one approach we can consider is the brute force method. The intuition here is straightforward: treat every possible path in the binary tree as a potential candidate and check if it matches the linked list. This can be achieved through a depth-first traversal of the tree, where we start at each node and traverse down the tree, comparing the node values with the linked list sequentially. If we encounter a mismatch, we backtrack and continue exploring other paths. Some key observations about this approach are that every path in the tree is treated independently, and the matching process involves traversing both the tree path and the linked list simultaneously. However, the time complexity of this approach can be expensive, as for every node in the tree, which is n nodes, we might traverse the entire linked list of length m. This results in a worst-case time complexity of n*m. The space complexity of the brute force approach is determined by the recursion stack used during the depth-first traversal, which is proportional to the height of the binary tree, denoted as h. This results in a space complexity of h. While this method is simple to implement, it becomes highly inefficient for large trees and long linked lists due to redundant checks on overlapping paths. To address this inefficiency, we can consider an optimized depth-first search approach that incorporates early termination. The intuition here is to build on the brute force method but to halt recursion as soon as we detect a mismatch. This saves us from unnecessary computations. The process starts at each node in the tree, and a helper function is used to recursively verify if the current path matches the linked list. If a mismatch occurs at any point, we immediately terminate the recursion for that path. Successful matching is achieved only when the entire linked list is traversed. By recognizing that paths in the tree are independent, this approach allows us to apply depth-first search separately for each potential starting node. The optimized DFS with early termination still has a worst-case time complexity of O and *m, as we may still need to compare the linked list against multiple paths in the tree. However, in practice, early termination significantly reduces the amount of redundant computation, making it faster than the brute force method. The space complexity remains O, h, where h is the height of the tree due to the recursion stack. While this approach is faster in practice, it still requires checking all potential starting points in the tree. Another alternative to consider is a dynamic programming-based approach, which uses pre-processing to optimize the matching process. This method involves creating a prefix table for the linked list, similar to the pre-processing step in the Knuth-Morris-Pratt string matching algorithm. The prefix table helps track partial matches efficiently during the tree traversal. By reducing subpath matching to a pattern finding problem, we can skip redundant comparisons. However, this approach introduces additional complexity. The time complexity is O, n plus m, where m is the pre-processing time for the linked list, and n is the traversal time for the tree. The space complexity is O, m plus h, accounting for the prefix table and the recursion stack. After evaluating these approaches, the chosen strategy is the optimized DFS with early termination. This approach strikes an effective balance between simplicity and efficiency. While the dynamic programming method is faster in some cases, its added complexity and pre-processing overhead may not always justify the performance gain, especially for typical problem inputs. On the other hand, the brute force method is too inefficient for practical use due to its redundant checks. The key insight, or aha moment, behind the chosen strategy is recognizing that early termination in DFS avoids unnecessary work, making this approach naturally suited to the problem. It is simpler to implement than the dynamic programming alternative and handles large inputs more efficiently than brute force. The trade-off is that the worst-case time complexity remains O and *m, but the practical performance is often much better. This balance of simplicity and efficiency makes the optimized DFS approach an ideal solution for this problem. In this problem, we are tasked with determining if a given linked list is a subpath of a binary tree. To clarify, this means we need to find a downward path in the binary tree where the sequence of node values matches the sequence in the linked list. To approach this, we'll start by understanding the structures involved. A linked list is a sequence of nodes where each node points to the next, while a binary tree consists of nodes where each node can have up to two children, a left and a right. Our goal is to check if there's any path in the binary tree starting from any node that matches the linked list exactly in sequence. To solve this, we'll define a recursive function called isSubpath. This function will check if the current tree node matches the current linked list node. If it does, we'll recursively verify the left and right subtrees to continue the matching process. Finally, the main function will traverse the entire binary tree, starting at the root, and call a helper function to check each possible path for a match. At each node of the tree, the helper function matchPath plays a crucial role. It begins by handling two base cases. The first checks if the linked list pointer is null, which means the entire linked list has been successfully matched, so we return true. The second base case checks if the tree node is null, indicating that we've reached the end of the tree path without completing the linked list match, so we return false. For the recursive case, if the current tree node's value matches the linked list node's value, we proceed to check both the left and right subtrees for the next linked list node. Beyond this helper function, we perform a depth-first search, DFS, to traverse the binary tree. At each node, we invoke the helper function to check if the linked list matches starting from that node. If no match is found at the current node, the DFS continues exploring other nodes in the tree. A few key insights emerge here. Recursive matching allows us to backtrack efficiently when a partial match fails. DFS ensures that we explore all potential starting points in the tree. Additionally, the algorithm can terminate early as soon as a complete match is found, optimizing computation time. Now, let's consider the data structures and the complexity of our approach. For the data structures, the linked list holds the sequence of values we are trying to match, while the binary tree serves as the search space where we look for a matching path. Additionally, the recursive stack, which is an implicit part of the recursive function calls, allows us to explore all potential paths in the binary tree. In terms of complexity, the time complexity is O, n asterisk m, where n is the number of nodes in the binary tree and m is the length of the linked list. This accounts for the possibility of needing to check every tree node against the entire linked list. The space complexity is O, h plus m, where h is the height of the tree and m is the length of the linked list, corresponding to the memory used by the recursion stacks. It's also important to handle edge cases carefully. For example, if the linked list is empty, we return true since an empty sequence is trivially a subpath. If the binary tree is empty but the linked list is not, we return false as there's no path to match. Additionally, mismatched values or single node cases require special handling to ensure the algorithm remains robust. To illustrate how the algorithm works, let's walk through an example. Consider the linked list, 4-2-8, and the binary tree shown. We start at the root node with a value of 1. Since it doesn't match the first value of the linked list, we move to its children. At the left child, which is a node with the value 4, we find a match with the first linked list node. From here, we recursively check the left and right children. At the right child of this node, which is a node with the value 2, we find a match with the second linked list node. Continuing this process, we move to the right child of this node, which is a node with the value 8. This matches the third and final linked list node. Since we've matched the entire linked list, we return true. This path, 4-2-8, is a subpath of the binary tree, and the output is true. Through this example, we can see how the algorithm efficiently combines recursive matching and DFS traversal to solve the problem. Here, we start by defining two classes, list node and tree node, to represent the linked list and binary tree, respectively. The list node class has attributes for the value of the node and a pointer to the next node in the list, while the tree node class includes the value of the tree node along with pointers to its left and right children. Next, we create the solution class, which contains the isSubpath method. This is the main function that determines whether the linked list is a subpath in the binary tree. We first handle two base cases. If the linked list is empty, we return true because an empty list is always a subpath. If the binary tree is empty, we return false since there's no tree to search in. After these checks, we use a helper method called DFS to determine if the linked list starts at the current tree node. If it does, we return true. Otherwise, we recursively check the left and right subtrees to see if the linked list is a subpath in either branch. The DFS function begins by handling the base case where the linked list has been fully traversed. If the head is none, it means we've successfully matched all nodes of the linked list, so we return true. If the node is none, it means we've reached the end of a branch in the binary tree without fully matching the linked list, so we return false. Then, we check if the current values of the linked list node and tree node match. If they don't, we return false. If the values match, we recursively continue checking the next node in the linked list against both the left and right children of the current tree node. This allows us to explore all possible paths in the tree to see if the linked list exists as a subpath. Here, we start by defining the basic structure of our nodes. The list node class represents a node in the linked list, with an integer value val and a pointer to the next node called next. Similarly, the tree node class represents a node in the binary tree, with an integer value val and pointers to its left and right child nodes. Next, we define the solution class, where the main logic resides. The method isSubpath is our entry point, and it takes two parameters, the head of the linked list and the root of the binary tree. The first condition checks if the linked list is null. If it is, we return true because an empty linked list is always considered a subpath of any tree. Now, if the root of the tree is null, we return false since there's no tree to traverse. The next step checks if the linked list can start at the current tree node by calling a helper method, DFS. If DFS returns true, it means we've found a valid subpath starting from this node. Otherwise, we recursively call isSubpath for the left and right children of the current tree node. This ensures we explore all possible paths in the binary tree. Moving on to the DFS method, its purpose is to compare the linked list with a specific path in the binary tree. If the linked list set is null, we return true, indicating the entire linked list has been successfully matched. If the tree node is null, we return false because we've reached the end of a branch without completing the match. If the values of the current linked list node and the tree node don't match, we return false as the path cannot continue. However, if the values do match, we recursively call DFS for the next node in the linked list, checking both the left and right child nodes of the tree. This ensures that we account for all possible ways the linked list could continue along the tree. The method completes by returning the result of these recursive checks, allowing us to determine whether the linked list is fully contained as a subpath in the binary tree. Here we are tasked with determining if the linked list, 4-2-8, exists as a subpath within the given binary tree. To solve this, we start by comparing the head of the linked list, which is 4, with the root of the binary tree, which is 1. Since the values do not match, the linked list cannot begin at the root. Therefore, we recursively check the left and right subtrees. Moving to the left child of the root, we find a node with the value 4, which matches the head of the linked list. At this point, we invoke a depth-first search, or DFS, to verify if the rest of the linked list can be traced from this node. Within DFS, we compare the next value in the linked list, 2, with the left and right children of the current tree node. The left child is null, but the right child has the value 2, which matches. Thus, we continue the search along this path. Proceeding further in the depth-first search, we now compare the next value in the linked list, 8, with the left and right children of the current tree node, which is 2. Here, the left child is null, but the right child has the value 8, which matches the linked list. Since there are no more nodes left in the linked list to check, we have successfully traced the entire linked list within the binary tree. The recursion then propagates the result of true back up the call stack, confirming that the linked list, 4-2-8, exists as a subpath. Next, we examine a new example with a different linked list, 4-2-6, and the same binary tree. Starting at the root of the tree, which has the value 1, we compare it to the head of the linked list, which is 4. As the values do not match, we once again recursively explore the subtrees. When we move to the left child of the root, we find a node with the value 4, which matches the head of the linked list. This prompts us to call DFS to verify the remaining values in the linked list. Within the DFS process, we compare the next value in the linked list, 2, with the left and right children of the current tree node. The left child is null, but the right child has the value 2, which matches. We continue along this path to check the next value in the linked list, 6, against the left and right children of the current tree node, which is 2. The left child is null, and the right child has the value 8, which does not match the linked list. This mismatch causes the DFS to return false. After backtracking and exploring other potential paths in the tree, we find that no valid path matches the linked list, 4-2-6. The final output for this example is false. In the final example, we are given the linked list, 1-4-2, and the same binary tree. Starting at the root of the tree, which has the value 1, we find a match with the head of the linked list. This allows us to invoke DFS to check the subsequent nodes. Within the DFS, we compare the next value in the linked list, 4, with the left and right children of the root. Both children have the value 4, so we choose the left child and proceed. At this new tree node, we compare the next value in the linked list, 2, with its left and right children. The left child is null, but the right child has the value 2, which matches. Since there are no more nodes left in the linked list to check, the DFS returns true. The result propagates up the recursion stack, confirming that the linked list, 1-4-2, exists as a subpath within the binary tree. The final output is true. To analyze the time complexity of the isSubpath algorithm, we focus on two primary methods, the isSubpath function and the DFS function. Starting with isSubpath, this method traverses the binary tree recursively, checking whether the linked list starts at each node via the DFS function. If it doesn't match, it moves to the left and right subtrees. Let's define m as the number of nodes in the binary tree, and n as the number of nodes in the linked list. In the worst case, we visit every node in the tree, amounting to O(m) recursive calls to isSubpath. On top of this, for each node in the tree, the DFS function is called, which may require up to O(n) operations in the worst case. Combining these, the overall worst-case time complexity of the isSubpath function is O, m*n*****. The DFS function is responsible for verifying if the linked list matches a path starting from the current tree node. For each node in the linked list, the function may recurse into the left and right children of the tree node. While both branches are explored to some extent, we are only interested in one valid path. In the worst case, the recursion depth corresponds to the length of the linked list, which is n. Each recursive call involves operations proportional to O, n. When we combine this with the behavior of isSubpath, the overall time complexity remains O, m*****, as DFS is bounded by O, n, and is called O, m, times for each tree node. Now let's look at the space complexity, which is determined by the recursion stacks used in both isSubpath and DFS. For the isSubpath function, the recursion depth is directly related to the height of the binary tree. In the worst case, such as in a skewed tree, this height can be O, m. In a more balanced tree, the height would typically be O, log m. This gives a worst-case space requirement of O, m, for isSubpath. Moving to the DFS function, its recursion stack depends on the length of the linked list, n. This adds an additional O, n, space requirement. When we combine these, the total space complexity is the sum of these two contributions, O, m plus n, in the worst case. Let's analyze the best, average, and worst case scenarios for the algorithm. In the best case, if the linked list is empty, we can immediately return true, resulting in time and space complexities of O, 1. For the average case, the performance depends on the structure of the binary tree and the distribution of the linked list. For example, in a balanced tree with partial matches, the number of DFS calls is reduced. Here, the time complexity would fall between O, m, and O, m****, while space complexity would be O, log m plus n, for a balanced tree. In the worst case, such as a skewed tree with no matches and a long linked list, the time complexity becomes O, m****, and the space complexity reaches O, m plus n. A brute force approach, in contrast, would enumerate all paths explicitly, leading to significantly worse performance with a time complexity of O, 2 to the power of h***n, where h is the height of the tree, and space complexity of O, h plus n. The current approach improves upon the brute force method by optimizing path validation. Instead of enumerating all possible paths, it prunes invalid paths early using value checks. This optimization reduces the time complexity to O, m****, which is much more efficient for larger trees. To mathematically prove this big O analysis, we note that for each of the m nodes in the binary tree, the algorithm performs at most n operations, one for each node in the linked list during a DFS call. The total work is thus bounded by m***n, giving a time complexity of O, m***n****. Additionally, the space complexity arises from the recursion stacks, O, m, for the height of the binary tree and O, n, for the length of the linked list, summing to O, m plus n, in total. When solving this problem, there are several common mistakes to watch out for. First, failing to account for edge cases like an empty binary tree or an empty linked list can lead to incorrect results. Always make sure to test scenarios where one or both inputs might be empty. Another frequent issue is incorrect path matching. Don't assume that the linked list must start at the root of the binary tree. The problem typically allows the linked list to match starting from any node, so overlooking this can leave your solution incomplete. Inefficient recursion is another pitfall. Recursive calls without memoization can result in redundant computations, especially with large trees where subproblems overlap, potentially causing time-limit-exceeded errors. It's also important not to ignore the structure of the binary tree. Binary trees have a hierarchical structure that allows specific traversal patterns, so treating them like generic graphs can lead to unnecessarily complex solutions. Finally, in recursive implementations, be careful not to confuse the base case, like reaching the end of the linked list, with the recursive case, where you're matching subsequent nodes. Mixing these up can introduce logical errors in your solution. Now, in an interview setting, there are some key insights to keep in mind for this problem. Always start by clarifying whether the linked list must match a path in the binary tree from root to leaf, or if it can start at any node. This distinction is crucial for framing your solution. Additionally, be prepared to discuss the trade-offs between recursive and iterative approaches. While recursion is often more intuitive, it can lead to Stack Overflow for deeply nested trees. Iterative methods avoid this issue but may require extra data structures. Another important tip is to optimize early by identifying overlapping subproblems. Using dynamic programming or memoization can significantly reduce runtime for larger inputs. Pay attention to constraints as well, such as the maximum length of the linked list or the size of the tree, which can sometimes reach up to 10,000 nodes. These constraints can help you identify feasible solutions that fit within the problem's limits. Finally, always test your solution with custom edge cases during the interview. This is a great way to catch potential bugs and show your thoroughness. Related problems, like PathSum or PathSum2, can also provide inspiration for similar approaches, so it's worth being familiar with them. There are also several alternative approaches you can consider for this problem. A brute force method involves checking all paths starting from every node in the tree. While this approach is simple and easy to understand, it's highly inefficient, with a time complexity of n superscript 2, or worse. A more efficient option is to use a recursive depth-first search, where you traverse the binary tree and attempt to match the linked list in the process. However, recursion poses the risk of Stack Overflow for deeply nested trees. To address this, dynamic programming with memoization can be a powerful alternative. By storing results for overlapping subproblems, you can avoid redundant calculations, striking a balance between efficiency and correctness, though it does increase space complexity. Another option is to use iterative DFS or BFS with a stack or queue. This approach eliminates the risk of Stack Overflow, but it may require more careful bookkeeping to track the state of your traversal. Ultimately, the choice of approach involves key trade-offs. Recursive methods are often faster but consume extra memory due to the call stack, while iterative methods are more space-efficient but can be slightly slower. Similarly, brute force is conceptually simple but impractical for large inputs, whereas optimized solutions are more efficient but demand careful implementation. Understanding these trade-offs is vital for selecting the best approach based on the problem's constraints and requirements. Great job! Today, we tackled the fascinating problem of finding a linked list within a binary tree. I hope the explanation and approach gave you greater clarity and confidence. Remember to keep practicing and exploring variations of this problem. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!